All right, in this module we're going to talk about X-ray fluorescence spectroscopy, and we're going to look at the two different ways we can do this. So just as a refresher, X-ray fluorescence spectroscopy, or XRF. So this uses high energy primary X-rays. And those X-rays excite the emission of characteristic X-rays. So these characteristic X-rays, which we talked about last period, are what we're trying to excite. And so it uses those characteristic X-rays to analyze the chemical makeup. Or composition. So basically XRF or X-ray fluorescence spectroscopy is using X-rays as the primary and also using X-rays, the secondary or produced characteristic X-rays, to analyze. And so there are kind of two different strategies that we can analyze these results, and it breaks down to the two types of spectroscopy that we end up doing. So the first one is known as WDS, or sorry about that. That should be wavelength dispersive spectroscopy. So that's WDS. And so this technique uses single crystal diffraction, so what we've talked about with XRD, to detect characteristic wavelengths emitted. And so we need to scan over a range of theta angles according to Bragg's law. Spelling today is not going great. So effectively, the thing that we're using to analyze the chemicals in this type of spectroscopy is the wavelength of the characteristic X-ray. And so we do that through Bragg's law. And so we have a single crystal and we use Bragg's law. So I'll go into more detail on this, but let me mention the second one real quick. So the second one is EDS. So this is the more common one I talked about last time. This is energy dispersive spectroscopy. And so when we're talking about X-ray fluorescence, X-rays are a primary beam. So this isn't not exactly the same as what's in an SEM or a TEM, both those electron microscopes, because those require an electron beam. And so that's the primary difference. Everything else about the spectroscopy is the same, though. But this is when we still have X-rays as our primary source. So the major principle here is the same, but the source of the incident beam is X-rays. Electrons that we have for these two. So that's the important thing to mention. And so with this, we have a detector that is a silicon lithium diode and this separates X-rays by their energies. Sorry about the spelling today. So the main difference here is with WDS, we're looking at wavelengths. And to do that, we need diffraction, and basically single crystal diffraction. And that gives us wavelengths. Whereas here in energy dispersive, we're using energies to separate out what element is what. And so that is a different type of detector, different configuration. So both give you similar information, but they're using a different principle to do so. All right, so next we're going to kind of go in more detail on this WDS, wavelength dispersive spectroscopy. All right, so let's go into a little bit more detail on WDS. So chronologically, WDS was the first technique. And that was before EDS. So EDS has kind of surpassed it in terms of how common it is, but WDS was actually the first one. So WDS provides better resolution and a wider range of elemental analysis than EDS. So there's definitely some advantages here. But the instrumentation is more complicated. So you saw in the previous about how we have to effectively have single crystal diffraction. And so a whole Bragg geometry, a whole diffractometer effectively has to be incorporated into this spectrometer. So there definitely is some additional complications here. So let's look at the wavelengths. So WDS can resolve relative changes in wavelength in the range of, and so this is change in wavelength over the wavelength itself, and so this is in the range of 0.002 to 0.02, and so this kind of corresponds in terms of energy to 0.01 to 0.1 keV. And so that's kind of your reference to EDS. So effectively, this is approximately 1 order of magnitude better than EDS. So that's something that's definitely going to come back when we talk a little bit more about EDS as well. Additionally, WDS technique can detect elements from carbon, so that's atomic number of 6 and higher. So EDS is actually getting better and better about detecting these light elements, but historically it's had some challenges with the light elements such as carbon and definitely anything under that. Okay, so let me switch over to the slides and I'll walk you through the WDS instrument and talk about some of the various components. All right, so this is figure 6.6 in our textbook. And this shows the main components that we have for WDS compared to EDS. So the top here is WDS, the bottom is EDS. So both of them, we have our sample here. We have a source, and it's both X-rays in both these cases. But it's really the detector afterwards. So WDS relies on Bragg geometry. So effectively we have a known crystal up here, and that is oriented with respect to the specimen with the theta geometry. And so our detector's over here. And so we basically set up a diffractometer from the x-rays that have come off the specimen. And so when we're looking at the detector, we are basically looking at intensity versus 2 theta. And so more or less, we're looking at an XRD plot of the characteristic x-rays that come off. And so we're able to evaluate their wavelengths from the 2 theta values and determine what materials we have. In EDS, it's different in that the characteristic x-rays that go towards the detector, in this case it's a silicon lithium diode, this basically sort of splits apart the characteristic x-rays in terms of their energies. And so we get intensity versus energy of the characteristic x-rays, and we're able to evaluate the energy of those x-rays as opposed to the wavelength to be able to get very similar information. Okay, so let's look at WDS specifically. So this is a closer, more detailed view of a WDS instrument. And you see that we have several components that we just talked about, but in a little bit more detail. So it contains, the detector is the main thing that we want to go across. So we have the X-ray tube and the filter like we have in previous experiments. But over here, where we have basically the diffractometer, is the additional component. And so we have what we call an analyzer crystal. And so this is our known single crystal that allows us to evaluate the wavelength because we know the despacing. And so we can calculate the wavelength because we know despacing and we know the angle. And so that is kind of a reverse of diffractometer that uses a known wavelength to get the despacing. So we're kind of doing it in reverse there. So these photons that come in from the sample go through the same collimator that makes them more parallel, and then goes through the analyzer at that angle theta, and then those that are diffracted go to the photo counter as intensity in the same geometry that we see there. And so the reason that there's some complication is obviously this kind of puts two pieces of equipment together, a diffractometer and the spectrometer. And so it's complicated because we have to scan over a range of theta values just like we did for diffractometers. And so that means that if we only have one analyzing crystal, that means that we have to scan through the entire range, and that can take time. And so WDS tends to be slow and sequential because we have to do at one spot we would have to look at we scan through an range of those theta values. We can get around that, and some of the more modern instruments have multiple channels, what they call multiple channels, but really what that means is that we have multiple analyzer crystals. And so that allows us to do multiple in parallel instead of sequentially. So that's one way we can get around this. All right, so let's talk a little bit more about this analyzing or analyzer crystal. And so this crystal needs to be carefully selected because it affects the range of detectable atomic numbers that we can detect. So just like the diffractometer experiments, the choice of wavelength affected what kind of d-spacings you could calculate. The same is true here with crystal and what atomic numbers that you can select. So if we solve for this with what we're after, which is wavelength, if we solve Bragg's law, then what we get is that the wavelength is equal to 2d, so the d spacing, sine of the angle theta, over n. Right, and n was that order of fraction. So if we go by kind of the typical experiment, normally the max angle in WDS that we would deal with is 73 degrees. So that's, again, theta, not 2 theta. And so if you plug this in to this expression here, you get that the max wavelength is going to be on the order, and so it's going to be approximately 1.9 times the d spacing of the crystal. So basically, whatever your d spacing is for your analyzer crystal, double that, and that will give you your max wavelength in the same units. So let me show you a slide from the book. Okay, so this is table 6.4, which gives a list of analyzing crystals used in WDS. So we have some various crystals like this lithium fluoride with a certain plane orientation, lithium fluoride with a different one, this PE, this other TAP, or we can actually make synthetic microstructures which have much larger d spacings. So you can see here the plane spacing is on the order of 100 angstroms as opposed to on the order of single-digit angstroms. And so these various planes mean that this is 2 times d, and so this is our maximum wavelength that we can detect. So to sort of ask a question at this point, so you can pause your video after this, but based on these numbers that we have, so these are our plane spacing, which is 2d. So basically the idea here is what do these relative plane spacings, which one is required for detecting light elements? So of all the listings here, which ones do you think will be better at detecting light elements? And you can use the previous equations. You can also look in your book for some values for wavelength values there, but see if you can come up with which relative plane spacings are better for detecting light elements. Answer that question and we'll come back and we'll look at this. So to answer this question about WDS and what d spacings are required to detect the wavelengths of light elements, I turn your attention back to table 6.3 in our textbook, and this gives you the values of characteristic X-rays, wavelengths, and energies. And so if we look at some of these lighter elements, we see that they do not have L and M lines. They just have K. And if you look, they have really large wavelengths because they have really small energies. And so that means that we need the analyzing crystal with the basically which will give us the highest wavelengths possible. And so if I go back to that table, these ones here at the bottom have the highest wavelengths possible because that is equal to 2d according to the equation that we just looked at. So these layered synthetic microstructures are basically have been fabricated or synthesized to allow us to detect smaller and smaller elements because they have larger and larger wavelengths. So that's what I was hoping you'd get out of that. And so if I show you the rest of table 6.4, you'll see that. And so this kind of gives you the atomic number range that you can expect to analyze with a various crystal. And so with this one, which has the smallest plane spacing, you can only detect things titanium or larger. And then again, going down to this one, you can detect things like beryllium and fluorine, which have a low atomic number, and then obviously the different ranges in between. So this is why WDS can be very slow, is because if you want to be able to scan the whole range of atoms and elements in a spectrum, you often have to use multiple crystals. So this one will give you the low elements, slightly higher, and then slightly higher. So that's why it can be slow, because we have to use multiple channels to have multiple analyzing crystals, or we have to do them sequentially. All right, so we just saw that an analyzing crystal, sorry about the handwriting here again, must have a large d-spacing to detect light elements. So we just saw that with our examination. So those layered structures were able to detect things less than 9. On the other hand, if we look at another parameter with these crystals, so an analyzing crystal with small d-spacing will have higher resolution. So these give us better resolution, and that's due to an increased angular dispersion. And so we can kind of illustrate that by looking back to a differential form of Bragg's law, which is the change in angle here with respect to the wavelength is equal to n over 2d sine theta. And so effectively that tells us that there's basically more angles in between when you have the higher d-spacing. So effectively it's spread out and dispersed more when you have smaller d-spacings. And so that's a good thing. So basically the smaller the value is here, the larger this dispersion is. And so that means that things won't be as close together and we can resolve them better. That's what we mean by this increased angular dispersion, illustrated by this equation here.